Thanks everyone for coming to the SCFT in Physical Mathematics seminar. We're delighted to have Mitch from KAIST. And he's going to tell us about the extended vertex algebra of 4D n equals 2 SCFTs and their higher products. Take it away.
Awesome. Yeah. Thanks, Rob, for the introduction and for the invitation to give a talk here. It's an opportunity I'm very happy to have. And yeah, I hope to instill some stimulating kind of reverberations that come about from this. Yeah, this is work I've been doing with my former PhD advisor, Philip Argyris, who's at the University of Cincinnati, and also his former graduate student, who's my sort of academic brother, Matteo Latito, who's with me at KAIST at the moment and is on his way to IFT Madrid over in Spain after the summer. And this talk is going to be mainly based off of a paper that came out about 2 years ago in the fall, and going on 3 years now, and hopefully a paper or two that's going to see the light of day maybe next month. Maybe this should be plus or minus one. Who knows? These things have the tendency to get away from us. But yeah, with that, let me get started here. And before I get going, yeah, feel free to interrupt with any and all questions. I kind of welcome any kind of spontaneous engagement here. So yeah, feel free to just like chime in if you have something you want clarified. Okay, so let me start off with some motivations and goals for this kind of the project and our whole goal here, which is to basically find a universal set of BPS extended operators that exist in all 4D n equals 2 superconformal field theories. And in particular, assuming that we can actually accomplish this goal, we then want to study their operator product algebra, i.e. their fusion. We want to study their correlation functions with themselves and perhaps with local operators. And if they're of the sort of defect type of extended operator, we want to go ahead and study their sort of defect properties, i.e. their sort of local operator algebras that only have support on the word volume of the defect. And if they are of this particular type of extended operator, we then want to go ahead and study the interactions that take place between the local operator algebra and these defect local operators. And our approach for doing this is going to be the following. We want to try to identify a relation between extended operators and a particular universal local operator subalgebra that exists in every 4D n equals 2 SCFT. And in particular, this local operator subalgebra is a Susy projected subalgebra, and it has the structure of a vertex operator algebra. And our method for doing this is to apply what's called the descent procedure to the local operators forming this vertex operator algebra while working in Minkowski space. And you'll see throughout the talk, or I'll explain rather, why I'm emphasizing our sort of scene and setting here in Minkowski space. Okay, so let me go over a quick recap of this local operator subalgebra with the structure of a VOA. So we're basically building upon the following key result, which was found in 2013 by Beam and Company, which is that there exists a vertex operator algebra, which I'll call throughout the talk Chi2D, and every local unitary 4D n equals 2 SCFT, which I'll denote is this math-cal T sub 4D. And the way this VOA is identified within the 4D theory is by passing to the cohomology of two particular nilpotent supercharges, which are typically called Schur supercharges. And there's like two types, which throughout the talk I'll call one of them T plus, one of them T minus. And if you're at all familiar with sort of a common sort of notation for denoting the supercharges in these theories, that this is the particular linear combination of supercharges that we end up working with. But the thing to point out is that this choice of T plus minus for these nilpotent supercharges that pick out the VOA is not unique. It's I've simply made this choice to pick out a particular Euclidean subspace of space-time that supports the VOA. But there's sort of a sort of strata, you might say, on the nilpotent variety of 4D n equals 2 SCFTs. And on this particular strata, you can pick any two elements, and they'll be related to the T plus and T minus sort of by a conjugation. Okay, so this T plus cohomology picks out two things. The first is that it picks out the set of twist translated Schur operators as being those which form this vertex operator algebra. Where a Schur operator is just a particular type of 4D local operator that's annihilated by these nilpotent supercharges T plus minus at the origin. And when you combine this with their 4D selection rules that that sort of define the way in which these Schur operators are BPS, it implies that when you consider their correlation functions move about in this plane in a particular way, the results are meromorphic functions of only their Z insertion points. And the second thing this T plus cohomology picks out is an SL2Z sub-algebra of the 4D conformal algebra, which acts on our set of Schur operators as symmetries. Looks like my slide is a little cut off here. This could be my mistake. But regardless, I'll just say in words whatever's missing down below. At this point, the fact that this T plus minus cohomology picks out these two pieces of data already tells us sort of in a sort of canonical fashion that this chi2d has the structure of what's called a quasi-VOA. But somewhat miraculously, it turns out that this SL2Z is actually enhanced to the Virasoro symmetry due to the existence of a conformal element, which comes from a universal Schur operator that lives in the 4D theory, which when you sort of pass to the cohomology ends up organizing all these Schur operators into Virasoro primaries and descendants. And so in the end, this is what gives us this set of Schur operators, the structure of VOA. And what's getting cut off here is just a sort of physicist definition, if you will, of what I mean by quasi-VOA, which basically is just a generic vertex operator algebra that doesn't have a conformal element, that is to say a Virasoro stress tensor. But it still carries a representation of SL2Z that will organize my spectrum of chiral operators into 2D conformal primaries and descendants. Yeah, so hopefully that it doesn't happen throughout the talk here. Any idea why that's going on? Maybe I can zoom out a little bit. Okay, we'll try this.
You need to click on it again before you can use the click.
Oh, interesting. Still, okay. Anyways, so a key feature though of the VOA is the following. If we take the VOA to have support in the Euclidean two-plane, which is what I said we're going to do, and throughout the talk, my spacetime is always just going to be in flat space and it's just going to have the topology of R4. But once you do this, make this assumption that you're going to choose your supercharges such that it's living in a particular Euclidean two-plane, it immediately implies that it's going to be independent of working in Euclidean versus Minkowski space, where either one of these choices is effectively what's determining the signature on the two-plane that sits orthogonal to this two-plane supporting the VOA. And for reasons that will become clear throughout the talk, I'm going to end up working in Minkowski space. So I'm going to take this orthogonal two-plane to have a signature 1-1. And just to kind of build some geometric intuition here so you can kind of visualize what's going on in the ambient 4D spacetime, I'm going to, throughout the talk, work in these complex light cone coordinate system here where x plus minus denote my light coordinates and z bar are going to be the complex coordinates parameterizing the x3, x4 plane, which is this 2D Euclidean two-plane supporting the VOA. And I'll frequently make reference to pictures like the following, where coming out of the board, I have this Minkowski two-plane, and orthogonal to that, I have this VOA plane. And in terms of what we just went over, I basically just said that we can take these Schur operators, I can put them in this VOA plane, moving them about in a very particular way, which I'll review. And what you find is that when you look at a correlation function of these Schur operators, they're meromorphic functions of their Z insertion point. Okay, so now I'm just going to give a kind of light overview of the main results that I'm going to go over today. So in our paper from a couple of years ago, we showed that there exists a universal extension of this vertex operator algebra to another vertex algebra, which at least has the structure of a quasi-VOA. And we call this the extended vertex algebra of the VOA that's associated to this generic 40 n equals 2 SCFT. And this extended vertex algebra is realized by including the extended operators that are constructed from Schur operators via sort of generalized version of what is typically known as the descent procedure. In this this particular cohomology setting. And what we find is that for every Schur operator, we can apply this descent procedure, and it's going to output a web of non-compact extended operators, which I'm denoting here by D with a superscript n, where n labels just the word volume dimension of the extended operator that's produced, and they're either going to be 1 or 2 dimensional, so we're going to either get lines or surfaces. And in a sort of canonical fashion, these descent operators are going to be both T plus, and there should be a minus here. They're going to be both T plus and T minus closed. And this is the sort of descent web. So for each Schur operator, I can perform this descent procedure in different ways, and I'll either get a line operator called O plus, a different line operator called O minus, or I'll get a 2D surface operator called S. And as I mentioned, what we find is that when you consider the correlation functions in OPEs of sort of all of these cohomology classes thrown together, they're going to sort of canonically have the structure of a quasi-VOA. And I will address whether or not this also gets enhanced to a bona fide VOA as we move along here. But something I do want to emphasize is that we did recently come to understand and prove that this descent web is sort of unique and complete in the sense that in applying this more generalized version of the descent procedure in this setting, you're not going to get any new sort of cohomology classes. So we can sort of make the claim that we're not missing any cohomology classes that come from this generalized descent procedure, which is a very nice result we're happy about because it took a little while because you have to sort of play around with these integral equivalence relations that relate the different possible descent operators that you can get in this setting. But an important point is the following. These descent operator OPEs are capturing local operator OPE data that's beyond that contained in the VOA of Schur operators, which sort of by definition is only going to contain OPE data among the SG2R multiplets of Schur operators. Actually, this might seem a little mysterious at this point because I have not told you how this SG2R emerges, but hopefully once I get to the appropriate slide, this will ring a bell. And if it doesn't, then I can come back and explain. But the reason for this is the following. Based off the definition of these descent operators, their OPEs essentially require OPE data, not from Schur operators, but from their superdescendants. And in particular, if we're looking at the OPEs for a descent operator with a Schur operator, it's going to require us to consider the local operator OPE data between very particular superdescendants of Schur operators with Schur operators. And in the case of a descent-descent OPE, it's going to require us to understand the local OPE data between these different superdescendants of Schur operators. And when you combine these two above facts with the following well-known fact about just superconformal representation theory, which says that the OPEs of superconformal multiplets are not generically determined by the OPEs of their superconformal primary, it's essentially telling us that this extended vertex algebra is indeed accessing more physical data about the theory that we're performing this cohomological reduction within relative to the VOA. So it's a very nice feature because we are indeed kind of accessing more physical information, which is ultimately what we want. And currently, our goal is to try to understand precisely what local operator OPE data of the physical theory we're accessing with the extended vertex algebra. And an equivalent way of saying this is we want to know what are the cohomology classes that can appear on the right-hand side of these extended vertex algebra OPEs. And our current approach for doing this, which is very much a work in progress, and I'm not going to go into very much detail on it today, but if any of the words or perhaps cryptic statements that I end up making about it or get you excited at all, please come talk to me offline about it. But our current approach is the following. We want to construct what I refer to as higher products in this cohomology theory that capture the extended operator cohomology class is appearing on the right-hand sides of our extended vertex algebra OPEs. And by higher products here, all I mean is higher dimensional versions of lambda brackets that one typically defines in 2D chiral algebras that sort of organize the set of local operators that appear in the singular terms of your OPEs in that setting. And the existence of higher products or these higher dimensional versions of lambda brackets in this setting, what it does for us is it ends up opening up the door for sort of an alternative route towards a kind of SL2Z symmetry enhancement within the EVA, which if it does occur, it will occur in a fashion that's very similar to how analogous symmetry enhancements occur in some other well-known twists, mainly the minimal twists that come from, say, a 4D n equals 1 theory or a 3D n equals 2 theory. And I'll say some very kind of brief remarks at the very end of the talk if I get to it and have the time on this current approach.
Question.
Go ahead, yeah, please.
So when you say higher dimensional version, does it mean you're considering multi brackets, like brackets, multiple inputs, or are you considering multiple lambdas?
Great. I mean neither, actually. I'm talking about binary brackets with one lambda. And higher here just means that the sort of surface supporting what I would want to call the mode is sort of extended into the ambient 4D spacetime. That's all I mean.
Does it feel like a shifting degree brackets?
Some of them do, yes. We can define, yeah, there is, we do have something you would want to call the cohomological degree. In our case, it basically functions as the U1R symmetry of the 4D theory. And some of the brackets do, some of the brackets don't. So, yeah. Yeah, great though. Does that, yeah.
Sounds like it's a defining additional algebraic structure.
Yeah.
It's like awesome.
If it, yes, no, good. Yeah, you're saying all the right words. And this is precisely a question that we want to know the answer to because I'm getting a little ahead of myself here, but you might appreciate it. It's not clear because we're working in this Lorentzian setting that these brackets that we can define, which are effectively mode actions, end up satisfying the sort of lambda brackets that define these shifted Poisson vertex algebras that O and Yaki formulated a couple of years ago. If that's what I think you're referring to there, yeah. Yeah, I would love to talk about this more though. Yeah, but good. Okay, so now I just want to give a kind of really high-level geometric overview again, just to establish some geometric intuition here for what's going on. So here, the coordinate system here, I now have the VOA plane extending to the right. And orthogonal to it sitting in sort of the plane of the page is this Minkowski 2 plane, which is going to be where all the support of these descent operators is. And in the case of this L plus line operator I told you about, it's actually light-like. So it lives on this X plus light ray of this Minkowski 2 plane. And orthogonal to it, this L minus line sits on the orthogonal light ray, which we sort of take to be X minus, the X minus coordinate. And then we have our surface operator S, which fills this whole like Minkowski plane. And the thing to note about the geometry of all these descent operators is that based off how they're constructed from a Schur operator located at the origin, they all end up intersecting the origin of this VOA plane. And so what this means is that we can perform what's called a twist translation of them to separated points in the VOA plane, where here I have a surface operator located at the origin. I've shifted my L plus line. I have the L minus line and some other coordinate, and I have a Schur operator there. And what we end up finding is that when you look at a correlation function with all these different insertions in there, you get some new meromorphic function that only depends on the Z insertion points of the operators in question. And so what this is basically telling us is that these descent operators, L plus, L minus, and S, behave like chiral operators in some new quasi-vertex algebra, vertex operator algebra. And because the Schur operators are a universal subalgebra of every 4D n equals 2 SCFT, meaning if you give me any local unitary 4D n equals 2 SCFT, they always contain Schur operators, and that's precisely what I'm constructing these descent operators from. it's telling me that this QVOA is a universal extension of the VOA of Schur operators. Yeah, and then this just gives us what we end up calling the EVA. Okay, so here's a outline of the rest of the talk. What's going to come up next is an overview of the symmetry algebra that is picked out within this cohomology setting. And then I'm going to go over the properties of the descent operators and also go into some detail about their construction and this sort of generalized descent procedure that I made reference to. And then we'll go over an explicit example where I'll flash some of the OPEs for the quasi-VOA of a free hyper SCFT. And I'll try to highlight some of the important features and lessons that we can take away from that. And at the very end, if I have time, I'll make some kind of very scant remarks about this whole higher product story. But things in our understanding of what's going on with these are sort of in flux at the moment. And so many details are going to be left out. But again, I would implore you to come talk to me offline about them if anything I say sounds interesting. And then I'll conclude with some questions in future directions. Let me pause real quick. Any more questions, perhaps? If not, I'll march on. Good. So just a recap here of what is the symmetry algebra of these theories. So for any given 40 n equals to a CFT, the space-time symmetry algebra is this superconformal algebra SU2, which is a complex Lie algebra is SL4/2. It has a bosonic subalgebra consisting of the usual 40 conformal subalgebra and an internal U2R subalgebra, which we decompose into an SU2R and a U1R components. And then it also has a fermionic subspace containing supercharges that transform in both the fundamental rep of SU2R and either the left or right-handed spinor rep of the Lorentz algebra. And this is how I already showed you an example, but this is typically how I will denote such supercharges, but you won't be seeing these too often. But in terms of commutation relations, all you need to know is that Q's and Q twiddles close on P's and S's with S twiddles close on the special conformal transformations of the 40 conformal algebra. Good, so what is this symmetry algebra picked out in this cohomology setting? So the T plus closed subalgebra, it contains the full 2D conformal algebra that's given by an SL2Z factor and an SL2Z bar factor, which basically preserve this Euclidean 2-plane that supports the VOA. And in terms of the explicit 40 generators, the canonical sort of generators of SL2 are related to them in this way. But this SL2Z factor, they're going to generate the holomorphic conformal transformations in Z, and this SL2Z bar factor are going to generate anti-holomorphic conformal transformations in the Z bar coordinate. But importantly, all of these, the generators of the SL2Z bar subalgebra have to be twisted by some SU2R transformations so that they're actually T plus and minus closed. And it's precisely this fact, which is why I said that the correlators and OPEs of Schur operators are only accessing OPE data between the SU2R multiplet of a Schur operator, because basically when you act on a Schur operator at the origin with these guys, you're going to end up picking other elements or other components of its SU2R multiplet. But okay, so because these SL2 Z bar guys are T plus minus exact, it implies that they basically act like gauge symmetries in our cohomology theory. And what I mean by that is that if I take a Schur operator and I translate it in a particular way to an arbitrary point in the VOA plane, then the result is something that's just T plus and minus equivalent to the zero operator. So these basically have no effect on correlators and OPEs in the cohomology setting. And so this essentially spits out for us that the symmetry algebra is given by the cohomology of these nilpotent supercharges evaluated on our 40 spacetime algebra, which just means I take the quotient of everything that's T plus minus closed modulo everything that's T plus minus exact, and all that remains in the numerator there is this SL2Z bar factor. So this is our symmetry algebra. And what this means is that I can move any, if you give me any T plus minus cohomology class, so any operator that's basically T plus minus closed, I can move it about the VOA plane using what are called these twist translations, which the adjective twist here just means that I can't just use the L-1 generator that's going to move me in Z bar. I have to use its twisted version, which means I'm going to be implicitly activating this SU2R lowering operator. But after doing this, what you find is that a twist translated Schur operator obeys this sort of word identity that comes from the fact that this L-1 hat guy is indeed acting like a sort of gauge symmetry on the operator algebra. Good. And one thing to note before moving on is that there are actually additional T plus and T minus exact generators that don't coincide. And in particular, there's a sub-algebra, which I'm calling M plus, and another sub-algebra, which I'm calling M minus. And they are each nilpotent, and they generate conformal transformations that move points outside of the VOA plane. So they're sort of mixing the light-like in complex, or the light-like in the complex coordinates of the VOA plane. And whenever we're just exclusively focused on the VOA, we don't have to worry about this fact, again, because we're only interested in sort of the cohomology of the 4D conformal or the superconformal algebra. And so these guys never play a role in sort of the symmetry algebra of the VOA. However, when we go ahead and apply the descent procedure, they will basically serve as part of the main ingredients to performing this. And so they're very relevant there. And this is what we're going to get into next. So at the end of the day, after you go through the whole song and dance of applying this descent procedure, this is the output. And this is what I'm writing here is a sort of a generic form of each descent operator from the descent web I showed you in the intro, constructed from a given Schur operator at the origin. And after the next slide, it'll become more transparent why these things are defined in this way and where they come from. But really all that I would like to say now is that as cohomology classes, these are just particular representatives that one can take, and they're sort of nice representatives. Yes. And another thing I really want to emphasize, because this seems to be a feature of this cohomology setting, which is unique relative to other cohomology settings, is the following. These L plus minus descent procedures obey a rather mysterious property, which is that they end up being topological about the VOA plane, depending on which cohomology setting I'm working in. So in particular, if I'm, say, working in T plus cohomology, that actually implies that this L minus descent operator is arbitrarily localizable about the VOA plane, which means that its world volume is sort of topological above and below the VOA plane. And this means that I can effectively, when I go about computing things, I can essentially use the right-hand side definition of L minus in T plus cohomology when I want to compute things. But really, what this is sort of saying is that L minus, it really becomes very close to just wanting to be a Schur operator that sort of lives on this X minus light ray. And the reason for this has to do with a sort of a fact about some exact relations involving your operator spectrum. And the basic statement is that the integrands of either L plus or the L minus descent operator is actually T minus or T plus exact in a discontinuous fashion about the VOA plane. And this is why, despite the fact that this integrand is everywhere along the light ray, T plus exact, because it's discontinuous about the T plus exact relation, because it's discontinuous about the VOA plane, it sort of allows for this guy to still be a good T plus cohomology class. So this is something I just haven't seen in other settings where descent operators are constructed in a similar way and whatnot. So that's why I just wanted to point it out. But okay, so all of these descent operators satisfy the following properties, which in a sort of very natural way give us this quasi-vertex operator algebra structure when we combine them with the Schur operators. So first, they're all T plus minus closed and point like in the VOA plane. And this means that we can go ahead and act on them with these twist translations. And we also automatically get this SL2Z symmetry algebra, which is just descending from the 4D word identities applied to the integrands of these descent operators. And so basically by acting with the generators of the SL2Z on a descent operator, you move them inside their integrands. And because I'm just integrating a local operator, they act on that local operator, and I can use the 4D word identities to get this right-hand side. So then holomorphy then follows, which by holomorphy, I just mean Z-bar independence, follows just from the fact that each of these descent operators are T plus minus closed, and they obey these sort of these SO2Z bar gauge-like word identities, which I claimed that the Schur operators satisfy. And meromorphicity of their correlators and OPEs when they're sort of just translated to arbitrary points in the VOA plane, this follows from, again, some 4D selection rules on their integrands. And also you need to know what their sort of chiral weight is, which is given by the eigenvalue of this L0 generator of the SL2Z factor. And it's a sort of a brief computation to show that their chiral weight is equal to the chiral weight of the Schur operator they're constructed from. So you don't actually shift the chiral weight of the Schur operator when I perform this descent procedure. So basically the action of L0, at least in T plus minus cohomology, sort of commutes with the action of this descent operation. So the last thing that you're gonna want to ask about is whether or not we still get this Virasoro symmetry enhancement that did occur in the case when we were just focused on Schur operators. And the requirement for this is the following. It would mean we need to find some Virasoro stress tensor which could be dependent on our descent operators, but we want to find some new element of the extended vertex algebra that organizes both all the descent operators and the Schur operators simultaneously into Virasoro primaries and descendants. And so far, all the examples we've computed in, which are essentially just free field examples, they show us that the natural candidate that you want to initially test this out for would be the Virasoro stress tensor of the VOA, and it doesn't do the job. But we haven't ruled out the existence of perhaps a new a bosonic chiral weight equal to 2 flavor singlet operator from the extended vertex algebra that actually satisfies this this requirement here. And this is something that we're sort of actively trying to figure out and pin down, at least in these free theories, or we can just do everything by hand, albeit it can be a bit computationally intensive. Yeah, good. But in the case of the free hyper, I'll sort of be able to show you very explicitly why the Virasoro stress tensor of the Schur operator VOA ceases to act like a Virasoro stress tensor with respect to the extended vertex algebra. Okay, good. So now I want to go through some of the details behind this generalized descent procedure. Let me just remind you that the main purpose of this is the following. If you're given a nilpotent supercharge, which I'm just going to generically call Q here, being nilpotent squares to 0, the descent procedure is just a method for constructing Q-closed extended operators from Q-closed local operators. And this is this sort of procedure was sort of given to us by Witten in his cohomology field theory paper from around 1988, if any of that rings a bell. But okay, so here's how the sort of algorithm is run. We start with, we choose a Q-exact generator, which I'll call B. And being Q-exact, it means that I can write B as Q acting on another supercharge, which I'll denote Q sub B. So that just means that B is in the image of my nilpotent supercharge. And I also want a Q-closed operator, which I'm going to call E. And the superscript here is just denoting the fact that it can be n-dimensional, it can be a local operator, doesn't matter. I just want it to be Q-closed. And then this is the definition of the Q-descent operator of E. So let me kind of break this down. We first just take E here, which is defined on some fiducial world volume. And then I'm going to act on it with the conformal element generated by the group action of B. And then after that, I'm going to act on it with this supercharged Q sub B. And the placement of Q sub B relative to this group action is irrelevant because these guys commute. And then I'm just going to integrate over the sort of maximal domain that defines this group element, which is this I sub B. And we need to make two assumptions here, or one assumption rather. First, we want to assume that B actually moves the world volume of E, by which I mean B does not reside in the isotropy algebra of whatever fiducial world volume E is defined on. And this is a necessary, albeit not sufficient condition for the descent operator to actually give me something that will yield finite observables, mainly correlators and OPEs when I go ahead and actually do these integrals over I. And this integration region depends on the compactness of this element B. And when I take our nilpotent supercharge to be T plus or T minus, it will turn out that B here is always non-compact. So we can just take I to be the real line.
I've only ever seen B to be a translation, like a derivative. Why be more general? Are you going to use that?
Yes. So before we knew that this sort of descent web that I showed you was actually unique and complete, it did appear as if there were other sort of legs on the web that were generated by performing this descent procedure with exact elements that were not translations. And yeah, so this is why I call it generalized. But in the end, you indeed find the sort of common result that you just stated, which is that all these descent operators are still just defined by performing descent with translations. Yeah, but this took some work. Yeah, I can be a bit more specific once I if I remember, once I get to the flash the specific form of these guys in a moment, just to illustrate the point. But yeah. Okay, and so then given this definition of the Q descent operator, if we act on it with Q, it just takes a little algebra using all the facts that I just previously mentioned to show that you get the following boundary term, which just says take my T closed or Q closed operator E, I act on it with this B group element, and I evaluate it on the boundary of this integration region. And if these boundary terms vanish, by which I mean if this boundary term is actually acting like the zero operator when I insert into correlators, then that means that the descent operator is a new Q closed operator that's n plus one dimensional relative to the dimension of E. Now in practice, the question of do these boundary terms vanish is sort of delicate, and you have to just kind of go case by case to evaluate whether or not the thing you wrote down here that takes this formal form is actually going to give you something that yields finite results. It's a delicate question. But one of the things we usually want is so that you can invoke some asymptotic properties of correlators and unitarity, things like this, is you want these boundary terms to reside on the conformal boundary of space-time. This is always the case when in the setting that we end up working in. But despite that, it's not always sufficient, and you might actually require a regulator that is compatible with your cohomology to actually get a finite result. And we actually had to do this in our free field computations, and I'll point out precisely where. But when we let Q be T plus minus, you still can prove that some of these boundary terms vanish in very specific extended vertex algebra correlators. And it's precisely the extended vertex algebra correlators that contain a single descent operator insertion. And also, when we let Q be equal to T plus or T minus, what you find is that the descent operators, you can construct a rather rich pattern of equivalence relations that are generated by the action of this VOA plane preserving sub-algebra. And the details of this are in our paper from a couple of years ago, where we kind of go through the most general kind of descent operators that you can write down, where indeed I'm letting this B here be a very general element. And then by application of these equivalence relations, we can dramatically reduce the set of descent operators that you could construct. So yeah, if any of these details sound interesting, they're here. But what's not in here is this more recent result, which says that the final descent web is actually only has 3 elements in it. Okay, so let's go through now what happens when we actually apply this to our cohomology setting. And I'm gonna, in particular, just assume to use notation here that I'm just working in T plus cohomology. So we're just gonna apply the T plus descent procedure to a Schur operator. And this means I can let B be any element of this nilpotent sub-algebra I mentioned earlier called M plus, which contains these light-like translations, 2 different Lorentz boosts that mix either the plus or z or plus and z bar directions of spacetime, and these special conformal transformations, which are actually special conformal transformations in the x minus direction. And what you find is that up to these T equivalence relations, the unique descent operator is the one constructed from P plus. And furthermore, in sort of a very canonical fashion, given this definition, you can just check that L plus will satisfy all of these properties that lead us to conclude that at least the set of L plus descent operators on their own are sort of behaving like new local chiral operators in the VOA plane. And so when we combine them with the set of Schur operators, we're going to get some new quasi-VOA. And the reason why I'm just calling it a quasi-VOA right now is because I have not mentioned or commented on whether or not T Virasoro, which organizes my Schur operators into Virasoro primaries and descendants, continues to organize all these L plus descent operators in a similar way. But we'll get to that. So the next question you want to ask is, can you perform this T plus descent procedure further on L plus? And the answer is no. The result is trivial, and this is basically because M plus is nilpotent. And this means that if I go ahead and try to act on L plus with using a sort of generic T plus descent procedure, none of the elements in L plus are going to move this line any longer because they all commute with one another. But this is actually not the end of the story for the following reason, which I'm going to sort of build up in a couple statements here. So first, as I've mentioned, this VOA is also obtained from the cohomology of T minus, and from the perspective of the VOA, T plus and T minus are essentially completely equivalent. Their cohomology theories are completely equivalent. You don't notice any differences as far as the local operator cohomology or the symmetry operator cohomology, which we've already went through. However, as I also mentioned in passing, precisely where they differ is in their exact sub-algebras. So as I flashed before you a couple of slides ago, the additional T plus exact generators are not the same as the additional T minus exact generators. What this means is that you can go ahead, you can perform the T minus descent procedure on a Schur operator. You're going to get an L minus line operator, just like you got an L plus line operator. And it's going to satisfy all the similar properties, which will form some distinct, but sort of in a perhaps obvious way, isomorphic quasi-VOA in T minus cohomology. So, okay, that should be expected. But the following sort of magical accident occurs, which is that if I'm working in T plus cohomology, it turns out that L minus is T plus closed. And vice versa, the sort of opposite statement, if I swap pluses for minuses, that also holds. And the way in which, say, L minus is T plus closed is you don't have to evaluate any boundary terms. This is just a purely algebraic statement here. And so this is, this is the reason why I call it a sort of magical accident, because L minus is not a T plus descent operator, but nonetheless, in this sort of quixotic way, it forms a good T plus cohomology class. And I already kind of told you why, because of this T plus exact relation that has this sort of discontinuity about the VOA plane on it. But what this is basically telling us is that I can sort of simultaneously consider the L plus and the L minus descent operators with Schur operators and it's going to spit out some new quasi-VOA, regardless of whether or not I'm working in T plus or T minus cohomology. So again, even though there are exact sub-algebras here that we're making these descent operators with respect to are different, we nonetheless get a sort of T plus T minus symmetric algebra emerging. So this magical accent is actually an example of a slightly more general result, which is the following. If I take, say, a T minus descent operator, where the thing I'm performing the T minus descent procedure on is also T plus closed, then sort of in this algebraic way, one can easily show that T plus acting on this D minus is just going to be identically 0, regardless of what B is here. It doesn't have to be P minus like it was in the previous case. And you can, again, swap pluses and minuses and you get the same result. Well, what this means is if I take E here, my T plus closed operator, to just be a T plus descent operator, then I can go ahead and perform the T minus descent procedure on it and get back a new T plus closed cohomology class. And so this is just basically telling us that you can sort of mix these descent procedures to actually keep the descent story going and build up new extended operators in this way. So if you go ahead and do this and apply this for when E is take it to be L plus, this means I can perform the P minus descent procedure on it. And what you find is the unique cohomology representative is this T plus and T minus closed surface operator, which takes the following form that I mentioned a couple of slides ago. And we just sort of canonically define it to be the D minus, the P minus descent procedure applied to L plus. And just as it was the case with L plus and minus, S here will satisfy all the same properties to basically, that tells you that you can add it to what was the quasi-VOA formed from L plus, L minus in the Schur operators, and you'll get some even further enlarged quasi-VOA that exists in T plus or T minus cohomology. Okay, so now I'm going to head over to the example before I move on here. Any kind of questions about this sort of generalized descent procedure and how we arrived at the final descent limit there? Yeah, good. So yeah, what are the ingredients in the 4D n equals 2 free hyper that we need to be mindful of? First, there is a fundamental Schur operator, which I'm going to denote by QI, which comes from the superconformal primary of the free hypermultiplet. And the VOA that you get is the theory of a free symplectic boson that is strongly generated by QI. And then we also have its 2D Virasoro stress tensor, which is coming from the Schur component of the 4D SG2R current. And when you get all the normalizations right, it takes this very explicit form. And what we did is we computed all the OPEs involving the strong generator Q, the Virasoro stress tensor, and each of their L plus minus and S descent operators. And just to kind of give a little background on what's involved in actually computing these OPEs, you basically just have to compute many integrals and apply a rather rich and not fully well understood pattern of equivalence relations to sort of make sure that what you're getting on the right-hand side are good cohomology classes that you actually recognize. And the details of all these equivalence relations and the sort of game you're playing to perform this reduction into operators that you can recognize is going to come out in one of these forthcoming papers I mentioned at the very beginning, hopefully rather soon. Okay, but before showing you OPE tables, I just want to flash up the explicit form of these descent operators when they're written in terms of the Schur operators that I just mentioned. And so the only new thing I need to tell you about here are these psis, which are essentially the super partners of Q here within the free hyper supermultiplet. Yeah, we don't need to stare at these any longer, but I just wanted to kind of give you an explicit realization of how everything looks. Okay, so first here, I'm just gonna, like I said, flash up some of these tables. And in the first case, I'm just showing you the OPEs between the QIs and their descent operators amongst each other. And the first thing to point out is that all the OPEs are meromorphic, as we sort of hypothesized that they should be just based off the algebraic properties that they satisfied. And this asterisk is here in this entry of the table because there are some convergence complications that occur when one tries to compute the surface-surface 2-point functions, which is what gives us this term closing on the identity here. And these convergence difficulties are basically due to intersections between these surface operators that occur at space-time infinity, in particular on the light-like conformal boundaries of Minkowski space. And to get around this, we basically just had to take the result that you get, the 2-point function that you get, and at the level of the integrals involved, performed a Wick rotation to essentially let us utilize a Euclidean regularization of the integral. So this is actually something that we'd like to learn how to do directly in Minkowski space, which when things are appropriately regulated, we think definitely should be possible. Okay, moving on then. This is the OPEs that you get when you consider T and its descent operators with Q and its descent operators, and they all take this sort of Virasoro-like structure, where V here is one of the fundamental, is either the fundamental Schur operator or one of its descent operators. And the immediate question you want to ask is there an operator which behaves as a new Virasoro stress tensor, so our quasi-VOA gets enhanced to a VOA? And the answer is no. What you find is that, at least individually, none T and neither any of its descent operators act like an individual stress tensor. And this is because a necessary condition is that the VI that's occurring on the right-hand side here needs to be equal to the YI that is in the input here. And at least in these entries that are outlined in red, you can see that that's not the case. So in particular, if we look at the OPE of S of T with Q, you see that it's not closing on Q, it's closing on S of Q. And so this is basically telling us that the modes of this guy are not mapping Q back to itself. And so S of T is not acting like the Virasoro stress tensor of Q, which by contrast, that is indeed the opposite is the case here between the OPE of T with Q, as it should be, because T here is the stress tensor of the VOA formed by Q. But we actually find a stronger result, which is that if you sort of consider a general linear combination of T and its descent operators, there does not exist a linear combination that actually acts like a Virasoro stress tensor either. Now, there are some, at least in the case of the free hyper, some ways around this, because we haven't examined all possible chiral weight equal to 2 operators that one could construct. And in particular, there are many chiral weight equal to 1 or 2 flavor singlets that one can make from these fundamental operators of the EVA, which are essentially just like generalized kind of Shigawa type operators, where you normal order these V's together, at least 4 of them in a variety of ways, and just contract them with epsilon tensors to make them singlets. And so we still need to sort of verify that there is no linear combination among those kinds of operators that can give you a new Virasoro stress tensor. So there's still some hope, is our conclusion, but even if there exists a new Virasoro stress tensor for the EVA, it may not actually end up being a universal feature, which would be a rather interesting result. But there is a sort of important check that we're currently doing, which is we can just try to find a 4D theory whose VOA only contains the Virasoro algebra, essentially is just equal to the 2D Virasoro algebra. And if indeed we can rule out, so in this setting, the only chiral weight 2 operators are going to be T and its descent operators. And if this first bullet point still holds in that case, then we've effectively ruled out the possibility for there to exist a new Virasoro stress tensor. And the simplest example where you could go ahead and play this game is with the free vector, which is, as I mentioned, something we're actively checking now. Okay, and last table of OPEs here are between T and its descent operators with themselves. And consistent with the previous conclusion, we find that there's no linear combination of any of these extended vertex algebra operators that sort of reproduce the Virasoro OPE on the right-hand side. But one thing to notice is that all the OPEs here are closing on normal ordered products of these U's, which are just the fundamental elements of the extended vertex algebra here. And so a natural question you might want to ask is, at least in the case of the free hyper, are these chiral operators sort of serving as strong generators of the EVA in this setting? This still seems possible, but it's quite difficult to answer because it requires some subtle null state relations at the level of the EVA, which at least in their 4D manifestation come from equivalence relations. In figuring out what these equivalence relations are is essentially the statement that we need to understand if these descent operations, at least in these free field cases, are acting like a derivation on normal ordered products of what is now uncovered. If they're acting like a derivation on normal ordered products of these fundamental operators of the extended vertex algebra. So yeah, I think I'm basically at the hour mark here, and I was going to go into saying some brief remarks about these higher products. Let me pause here, see if any questions about all the OPEs I just flashed, and if not, I'd be happy to go through this or just stop here. We could talk offline about it, but can I get like a couple more minutes? Is that all right?
5 minutes.
Okay, cool. So yeah, before mentioning then my brief remarks on the higher products, I just want to go over the bread and butter example where these lambda brackets occur, just to refresh the memory and to make the analogy more clear with what I mean by the higher products in this setting. So all the operators of the 2D chiral algebra are holomorphic, i.e. chiral, in the sense that they're annihilated by del bar. And this means that we can view the set of chiral operators as sort of conserved currents generating some infinite dimensional global symmetry of the chiral algebra. And in particular, conservation of these operators continues to hold after we multiply a chiral operator by any del bar closed function, which I'm calling rho here, and it's just you can just view as being some polynomial in Z or 1 over Z. And if I multiply this by a chiral operator, it's just going to give me another conserved current. And this basically allows us to define an infinite number of conserved currents, or conserved charges rather, which are typically called modes, that are associated to each chiral operator. And I'm denoting these conserved charges by O hats here, where n, the subscript n, just denotes the power of Z here that I'm multiplying the chiral operator by. And this integral is taken over just some cycle in the plane that's homologous to S1. And a feature of these modes is that they're topological, and they're going to act on other holomorphic operators or other chiral operators via linking in the following way, where if I insert this chiral operator A at the origin, then the mode action is defined by taking this integration cycle of O(n) hat and sort of linking the operator at the origin, linking A here at the origin. And we can go ahead then and collect all these non-negative modes into something akin to a generating function, which is typically called the lambda bracket. And it's just defined as follows, where instead of taking rho here to just be some non-negative power of Z, I just insert this e to the lambda Z, where lambda here is just some formal parameter, which is effectively parameterizing the different O(n) hats that I just showed you for n being a positive 0 or a positive integer. This is a nice little device because it's effectively in a sort of canonical way capturing the chiral operators that are appearing in the singular terms of O with A. So what we end up finding in our setting is the following. For each type of OPE occurring in the EVA, we can construct an analogous lambda bracket that's effectively comes from constructing the 2D modes of Schur operators and or descent operators. But there's a key difference between the 2D algebra case, which is that these modes have support on submanifolds of space-time that live outside of the VOA plane. And they reside sort of within the 4D ambient space-time. So they're not just localized within the VOA plane on these S1 cycles, but furthermore, they're also not defined on compact cycles within that are homologous to n-spheres within the 4D ambient space-time. And they're not defined on these compact n-spheres because one of the goals of these lambda brackets is to capture the T plus cohomology classes appearing in descent operator OPEs. But for us, we've already seen, at least in the case of the free hyper, that the things that the extended Vertex Algebra OPEs close on are more descent operators, which are defined on non-compact cycles. So that means they can't effectively be linked by n-spheres. And in particular, these are non-compact cycles that extend to the conformal boundary of Minkowski space. So the more appropriate notion of a mode in this case is one that's defined on some non-compact cycle, which is just not homologous to an n-sphere. And furthermore, I'm going to end with this extremely cryptic statement, which we're in the process of trying to break down and understand ourselves, which is why it's cryptic, but it's the following, at least the following claim, which is that the existence of these higher products tells us that there is a possibility for SL2C symmetry enhancement to occur if we can find higher products which are T plus minus equivalent to the action of essentially the topological symmetry operator that implements the Ward identity that says that L minus 1 acts like del Z on operators in the physical theory. Yeah. Again, this is cryptic. It requires a little more breaking down to actually understand what I mean by this. If you'd like to uncover it a bit more, I'd be happy to talk offline about it in a moment. But yeah, let me conclude here with some open questions and future directions here for where we want to take things and some of the things that are on our mind. So just to summarize real quick, I've hopefully convinced you that this extended vertex algebra is a new rich vertex algebra in every 4D n equals 2 SCFT that extends the VOA of Schur operators. And some open questions are the following. In terms of the structural properties of the EVA, we really want to be able to say something about it beyond it being a quasi-vertex operator algebra. In particular, one question you might ask is, does the QVOA, can you understand it as forming some kind of modules of the VOA? And the answer is yes, but as far as we understand the math literature, it's yes in a rather trivial way, because you can view the descent operators as forming sort of vertex algebra modules of the VOA in a canonical way, but they're not VOA modules, meaning they don't expect the fact that the VOA indeed has a conformal element. So this ends up being we're able to confirm such a statement, but it's not the one that is actually shedding any new light on the structural properties of the extended vertex algebra. Another question is on the finiteness of these descent operators, which is we'd love to prove that perhaps via some savvy cohomology statements that L plus minus and S always yield finite correlators and OPEs in interacting theories. This is not totally obvious when one goes about computing them. So we need to get our hands dirty in these more complicated real settings. And we'd also like to know if there potentially exists, at least in some examples, some finite strongly generating set for the extended vertex algebra. And this is an interesting question to ask because, and I didn't mention this, but for the vertex operator algebra of Schur operators, they are believed to always be strongly finitely generated. So we basically just want to know if that feature persists when you extend it to the EVA. And also, if anyone is familiar with these objects that have appeared in the literature in recent years of sort of studying formal aspects of conformal field theory called light ray operators, it might look like our L plus minus line operators are related to them. And this is something we're trying to also understand a bit more. And it would be nice if we could sort of import some of the techniques they use in these settings, which are very powerful for computing OPEs of these light ray operators in interacting settings. But it would, if it was true and we understood how the O plus minus guys were related to light ray operators, we could sort of leverage some of the techniques that are being used over here to import them to the interacting case where things become rather difficult. And last, we'd love to know if the extended vertex algebra contains any sort of geometry beyond the Higgs branch that's contained in its vertex operator algebra sub-algebra. Like for instance, we'd love to know if there's a sort of canonical associated variety that one can extract from the VOA that maybe gives us more data beyond just the Higgs branch that is a component of the moduli space of vacua of these theories. Okay, I will then and there, yeah, thank you guys for your attention. And yeah, I'd be happy to take any further questions or comments, etc.
Thanks, great talk. Any questions, Mitch?
You know what the extended view of looks for general Lagrangian theory? Right beyond just the hypermultiple?
No. We currently need to, yeah, finish up for the free hyper and the free vector, and that's right where we're headed. But yeah, you know, the unfortunate thing is that the number of possible like descent operators that you need to like consider, it's very large actually. And we probably need some computational assistance to actually do like extract OPE data and just compute things even perturbatively in those settings. And you know, we haven't figured out how to do this efficiently yet. And so yeah, this is directly where we're headed though. It's the next step. But it's a bit sort of unfortunate is that, you know, with where things stand even now, just understanding these things abstractly at the formal level, we don't even know if there's a good guess to make as far as what kind of quasi-VOA should they be, right? Yeah, and so we'd already just love to pin this down in the case of the free hyper and the free vector to understand how those two structures would be sort of, you know, combined in the case of a gauge CFT. Yeah, so yeah.
Also, Mia, do you have if there's anything known in the math literature about like extended VOA in the sense that you're talking about? You know, mathematicians have studied vertex algebras a lot. So
Right.
So you're claiming for a large class of vertex algebras, there is a universal extension. Seems to be a mathematically interesting statement.
Right. I mean, for what it's worth, yeah, I think I'm using the notion of extension rather loose here, right? All I mean is that you can just play with these things, and when you combine them together, they satisfy a set of properties, and you can sort of formally say that they form a quasi-vertex algebra. So in that sense, it's extending it. I don't know if it's actually the rigorous definition of an extension of a VOA in terms of like, you know, adding modules to it in that sense, which would correspond to like Virasoro primaries or something like this, like that give you like the non-vacuum modules and stuff like that. There are instances that we know about where there are some like rather strong statements about the module structure of certain VOAs that do occur for 4D theories, which is that some of them don't actually contain any extensions in terms of modules that are actually VOA modules. And so for those theories, that basically means that we would not be able to realize this extension in air quotes in terms of VOA module extensions in the strict math sense, which I think is what you're more referring to there, because they just don't exist for certain VOAs. So
I just wanted to pin down the precise mathematical structure that an extended VOA is. Is it an actual vertex algebra or what? That was the question.
oh yeah. Oh no, this is it's a bona fide quasi-vertex algebra. I mean, if you look up the definition of such a vertex algebra in, I think it's Franco Lupowski and missing one author from this 93 book, you can go down the list there, and this thing I'm calling the EVA will satisfy all these properties. So it is a type of vertex algebra that's been studied before. And we probably just need to give a little more effort to sifting through the math literature here to figure out what's known and not known on these more sort of rigorous notions of extension to such algebras. Yeah. So, yeah.
Cool. But no more questions. Thank you again.
See you.